Yep. Okay. You can't hear me. Okay. Let me see what I can do about this. Okay. Is that better? Is my audio coming through, or are we still dull here? It was clear before, but it was not. Okay. But at least it's on now, right? Okay. I'm trying a new webcam, and it is being a bit of a pain to start off with. So, okay. We will, hopefully this will go. If it drops out again, yell at me, and I will, again, try to click this back over and make this work. All right. So starting off with, John, you asked a question about forces, finding an unknown, finding the direction from adding a couple forces together. We'll get to that one soon as I just give you guys the highlights. Skipping through all this stuff, we've got streams coming up. We're looking at Mondays, and then once we get around the week of the 20th or so, we're doubling up. So we'll do Monday, Wednesday from then on until the exam. Speaking of the exam, it is on the 14th. Did you guys hear about this already? If not, this might be new. So the exam is going to be 2 free response questions, and that's it, which is crazy for taking this entire AP exam and turning it into just 2 questions. But this is what College Board decided to do. There's a 25-minute question on qualitative-quantitative translations and a 15-minute paragraph response. You get to take it on any device you want to. So you could do it on your phone. You could do it on your computer. You could do it, I don't know, iPad, tablet, whatever you feel like doing. It is considered to be open notes, which means that as far as College Board's concerned, they are assuming that you're going to look up all the notes and all the formulas and stuff like that, which means these questions are going to be a lot more focused on applying that knowledge than just getting that knowledge. So I wouldn't plan on anything getting a ton of points for like draw a free body diagram or derive this equation. I'm going to see it a lot more as explain why this works, ... Okay. Okay, so the qualitative-quantitative chunk there, this basically goes into explain something with words, then explain it with math, and then explain why those two are set together. So for example, you could be asked to look at a box that has forces acting on it. Actually, let's do one just to make this work and see if everything works here. So let's go through. All right, so let's assume we have a box. Which way is the box going to accelerate? Okay, yeah, so the left. Now, why? Why is that we're going to accelerate to the left? Okay, sure. So what you guys just described there was qualitative. You didn't use any numbers. You just simply said, oh, it's going to go to the left because the bigger force is pointing towards the left. That's qualitative. Quantitative might be something like saying, yeah, exactly. So that's all qualitative. So we're saying this is bigger. If you wanted to do quantitative, it would be saying something like, well, and let's say this is a 2 kilogram box. F equals MA. 15 minus 5 equals 2A. A equals 5 meters per second squared. And because I chose left as positive in there, this is the quantitative. Using numbers, using expressions, using stuff like that. So as long as, so this question is going to be something like, explain something using no numbers, and then explain it using math and say how they match up. That's what the qual-quant is going to be focused on for the most part. Right, that makes sense? Qual-Quant sometimes deals with data from experiments. Doesn't have to be, though. A lot of times they'll do like a theoretical, like, for example, a really good Qual-Quant one might be something like, we've got these two balls, they've got a mass m, and they're going to just be dropped. Actually, no, sorry. One's going to be dropped. One's going to be thrown sideways with some horizontal velocity, let's say 10 meters per second. And then they may ask you a question like, well, do they hit the ground at the same time? Assuming they're falling the same height and stuff like that. Your qual-quant one is going to be, yes, it's going to be there. They're going to hit the ground at the same time. Your quant part of that may be derive an expression for the time that it takes and get the t equals the square root of 2h over g. And then explain why they match up. And something like, well, there's no Vx term at all in here. So you could do stuff with experiments, but normally it's theoretical. It's find an expression, explain what's going to happen, and then how does the explanation, the logical process of what's going to happen, match up with the math. So is there a linear relationship? Is there an inverse relationship? Is there a term missing or not included in your final expression and then drops out? That's kind of what qual-quant is going to be jumping into with things like that. Okay, so while it's perfectly possible that they could have to do a data experiment collection sort of thing, where it's, here's this data, derive an expression, does it match that, explain why, sort of thing. Could be in there too. Kind of depends. Yeah, pretty much. That's exactly how I would justify this part. I would go saying something like, if I'm doing it with no math, I would say, well, they're dropped from the same height. They have the same acceleration because gravity's accelerating them at 10 meters per second squared constantly downwards. They have the same initial vertical velocity. We're ignoring air resistance, all that stuff like that. Therefore, they're going to hit the ground at the same time. The mathematical way, the quantitative way, would be, okay, y equals y naught plus dot, dot, dot. And get that expression, and then you say something like, hey, now we know, because this only depends on h and g, both of which are constant, and or both of which are the same for both these, and then we're good. So yeah, that's the kind of gist with Qual-Quant. It's do the math, then answer a question with no math, and then or answer the same question with no math, and then explain how you're saying the same thing both times. The paragraph length response is kind of like a regular FRQ. It's going to be something like, I had a good example here, like this one. Okay, this is one we're going to do later, but we can jump into it now. This would be a great paragraph response type question. So let's take a minute and see if we can figure out how to do this question. All right. All right. So any ideas on where we want to start with number 12, or with number 12 with this question? Any topics or ideas that we should really bring out here? Yeah, so John, that's really where we're kind of getting at here, is you brought up the idea of a system. So I guess the question here is, what are you defining as a system? And we really have a lot of options. There's the, I guess, best way of doing it, and then there's other ways. So let me preface this by saying, this is one of many different ways that you could solve this question. This does not have to be the way to do it. In fact, this may not be the best way to do it. Yeah, but what I'm going to do is, yeah, we'll talk about the boat and the fan. This whole thing is the system. So basically, you could say something along the lines of, okay, so I'm going to start off by basically saying, yeah, this is what we're doing. We're starting with, this is our system we're looking at. It's the boat and the fan. Okay. Then we could say something like, the only force going on here, as John mentioned, is an internal force. It's caused by something in my system acting on something in my system. Okay, so we add another part in here saying about how, no, so we've said this is our system we're looking at. We've talked about the forces there. Now we're going to bring in the theory. We're going to bring in the laws, the concepts, and stuff like that. Yeah. So in this case, Jessica, you're right. We probably should do a free body diagram here. Let me grab a pen. We're looking at the normal force. We're looking at the weight. Those two are balanced on there, and they would be caused by the surface and the earth, both stuff that is not in my system. The other forces on here that you can think about would be the fan and the sail. And those are internal. These are caused by something inside the system. Internal forces do not cause the motion of a system to change. So the boat fan system, the whole thing, will not change its motion because there's no external force. Okay, so we'd say something along those lines. Again, this is solving it, looking at it as a whole system. You could also do this by talking about the fan and the boat as two separate systems on there. Yes, and so yeah, if we look at John's example in the chat here, he's solving it looking at Newton's third law, action-reaction forces, which exactly is going to be another way of looking at this. So whereas I, in my definition, said the only force applied to the system is an internal force from the fan, John broke it up a little more, and that's perfectly fine to do. In there. And we're going through and talking about, he's talking about how the fan pushes on the sail, action, but the sail also has a reaction force pushing backwards the opposite way. Those cancel out. Yeah, in essence, it is Newton's third law is the reason this doesn't work. And we would have to have something like no sail here, grab the pen, no sail going on for us to have a actual change in its motion. Yeah, so Newton's third law is the reason that internal forces don't do anything and external forces are needed in order to accelerate it. So really, you could think about it, Newton's three laws, 1, 2, and 3, they're all saying the same basic idea. We need an external force to happen here for our motion to change. And if we don't have one, we aren't changing our motion at all. Oops, we have more questions. What else do we have here? Quant. Okay, so how do I know the sail and the fan forces are balanced? That is Newton's third law. So if we're doing this, let's FBD this for a second here. This is going to look at the fan, and then we'll look at the sail here. Okay, so the fan's going to push a force, let's say it's this way on there. Up and down are all equal. I'm going to ignore those for right now just for the sake of simplicity. But this is the force of the fan on the sail. That's going to be going that way on the sail. Okay, the sail also, actually, scratch that. The fan's putting a force on the sail. The sail, because of Newton's third law, is going to put an equal and opposite force on fan is probably not the right word. We'll call it boat. Because the fan is attached to the boat, the fan and the boat are one unit in this case. This force and this force are equal to each other. That is Newton's third. and therefore they're equal and opposite. They completely cancel each other out. And the overall free body diagram for the entire thing would look at gravity going down, normal force going up, and that's it. And because those are balanced, there is no other forces. There's no acceleration here. And that's this sort of thing we can get into. So yeah, this is a qual-quant, or sorry, a paragraph length response, typical one. They're looking for a paragraph. They're looking for 3, 4, 5 sentences going on here, starting with the claim that no motion, and then breaking down what evidence do you have to support this claim, and then why does that evidence explain your claim at all. So claim, evidence, reasoning or rationale for it. You can put assumptions in there if you need to, and go from there. Yeah, really, we can look at the air doing the transferring of those forces in there. So you could talk about the fan puts a force on the air, which puts a force on the sail, but leaving out the fact that we're assuming there's no energy lost between the fan and the sail into the air. We're going okay. So you could talk about the air's force in there. No, if there's not a sail, the boat definitely will accelerate. Let me get rid of my gobbledygook in here. Okay, if there wasn't a sail, then we look at our free body diagram and we say, okay, so we'd have gravity, normal, fan pushes the air, sorry, undo. Then we have the air pushing us to the left. The fan would push the air to the right. The air would push the fan to the left. Equal and opposite action, reaction. This way, we have an acceleration of that. Yeah, Newton's third law is one of those weird kind of, and frankly, the easiest way for me to think about it, and I teach my kids the same way, and they will still make this mistake. If you're talking about the force of A on B, fan on the air, then the third law equivalent is the air on the fan on there, or the earth pulling on the moon. The third law equivalent is the moon pulling on the earth. Me sitting in this chair, gravity pulls down on me, I push on the chair pushes up on me. So the chair has a downward force from me, I have an upward force from the chair, and then they all get balanced out in their free body diagrams. All right. Other questions on this one, or do we jump back in and find a different version? Okay, let me find a good one. Oh, I like this one. So we're speaking about qual-quant sort of stuff here. That was earlier. Okay, how would I know if it's quantitatively? So Sam, let's go back to that first example we did together here, where I had this terribly drawn box, and you guys all told me, hey, it's going to accelerate to the left, right? This is where we'd say, oh, the sum of the forces equals MA. You can find A dot dot dot. Okay, so that's the quant part, right? That's using the numbers. That's give me a number. You want to see qualitatively. Well, that also means if we're accelerating, we know V is not constant. Maybe we are having our direction change. Maybe we are speeding up. Maybe we're slowing down. All those indications are where we're going to get the idea that force must be unbalanced. So in this case, we have an acceleration going to the left that tells me there's an unbalanced force pointing to the left. Okay? And they may just say something like in the question, hey, we're speeding up, or we have a positive acceleration that way. That's the clue for how we're getting this qualitatively in there. Not giving us numbers, but saying that, hey, we are speeding up, or we are slowing down, or our direction's changing, something like that. Okay. So let me zip back up to my next example here. Not that one, this one. Okay, so this is stolen off a old AP practice, or no, this is actually 2015 AP1 FRQ. This is one that I could definitely see showing up as a possible qual-quant sort of topic, dealing with forces and stuff like that. So this sort of setup, it's an Atwood machine. It's 2 blocks connected with pulleys, and then say stuff happens. So they're going to start off by telling us the mass of block 2 is bigger than the mass of block 1. And we're going to let them go. What should happen in this case? Before we even get into the question, what are we expecting to happen to these blocks? Yeah, block 2 goes down. This one should go down. Block 1 should go up. And then there we go. Okay, so now let's talk big picture now. If block 2 goes down, what does that mean about the forces on block 2? They must be unequal. Good. Now, which force has to be bigger? The force going up or the force going down on block 2? Going down. Yeah. All right. And that's the gist of, John, you asked at the very beginning here, how do we know what the direction of a force is qualitatively? We just did it. That's the basic idea here. So on my free body diagram, I'm going to draw a nice arrow going down. And this is M2G, the weight of the block going downwards. Okay. I also have to draw a force going up. I'm going to call it T, and I'm going to make sure that it is less, that it is smaller than the force going down. Okay, so that's block 2. What about block 1? Which force on block 1 has to be bigger? Yeah, the tension's got to be bigger. Good. So now I've got block 1. Okay, now I have to draw this in here. And a hint about the AP. If they give you lines for something, they want you to use those lines. So is the tension for block 1 going to be the same, bigger, or smaller than the tension for block 2? They have to be the same, yes. So because I made my tension here 3 lines up, the tension for this case also has to be 3 lines up. They must be the same exact size. Otherwise, we would run into problems. Okay. So that must be the same length as that. Why are they the same? So there's a couple reasons they're the same here. The idea here is that the pulleys don't do anything other than change the direction. Okay, this is not the rotational motion sort of thing where these pulleys are huge and massive and take a lot of force to rotate. These are magical physics massless pulleys. They just change the direction of the force. They don't change the magnitude of it. Okay. So for other cases, if they mention the word that this is huge and massful and heavy and stuff like that, then we have to worry about the tensions not being the same. But right now, because this is a small, massless, frictionless pulley, all it does is change the direction of the force. So we take this force that was going up, and now it's still going up. It's just changing its direction over there. Okay. All right. Last force, block 1, M1G. How should I draw that one in? Yeah, so if you were on a computer, that's a great question. What I would do, what I'm assuming that the AP is going to have you do, or at least give you the option of doing, is to have a piece of paper in front of you, to draw it out on a piece of paper and take a picture with a camera. And then upload that picture and say, here's my free body diagram on there. That's my guess is what they're going to do. Because you're right, I can't think of another way to have you do these or derive these equations or stuff like that without having an actual either tablet or having a camera or something like that where you can take a picture. So I'm 99% positive you'll be able to take a picture of your work and upload it as proof that you've done this task. Okay. Yeah, so now smaller than the tension, good. It's downward. Smaller than M2G and smaller than T. Yes. So in this case, we really are kind of locked in here. This could be one line down. This could be 2 lines down. It can't be any bigger than what I have drawn right there. M1G must be less than tension, which must be less than M2G. So everything has to follow this set of setups right here. If it's not set up like that, we won't have a working system. Absolutely. Did it say? Okay, let me read the question here. The question never mentions that M2 is twice the mass. So as long as you have them M2G is bigger than M1G, we're good. If they did mention that it was twice as much, then we'd have to have those arrows be twice the difference. They will be that picky if they give you that information. So, yep, no problem. Okay, so that's part A. Part A, doing the free body diagram stuff. All right, part B, derive the magnitude of the acceleration of block 2. Express your answer in terms of those wonderful quantities, M1, M2, and G. Okay, there's 2 different ways of doing this part. And I'm going to do whichever way the first person in chat tells me how to do it. So, how would you guys go about deriving the acceleration of block 2? Solve for T on both blocks. Okay, so John jumped in with one possible way of doing it and substitute. Okay, so this is way number 1. I will do way number 2 in a second because way number 2 is a little bit clearer and easier, at least for me, but let's do way number 1 first. So this is way number 1. We're going to look at block 1. We're going to look at block 2, and we're going to get their Newton's laws for each of them. Okay, so for both of them, The sum of the forces on them must be equal to ma. Because they're connected with a string, their accelerations must be the same. And that's important. If these were just, I don't know, dealing with different magical connections, then we wouldn't have to worry about Okay, we back? Okay, good. Yeah, sorry. New webcam, it is being a pain in my butt and not the most useful thing in the world right now. So where were we here? So I've got, for M2G, we have M2G minus T equals M2A. So I've got my two Newton's law expressions set up for this sort of thing. As John mentioned, I'm going to solve one of these for T and plug them in. Now, I have to do that because T is not allowed in my final answer. I can't just do M2 or M2G minus T over M2 equals that. You guys can't see that work. Is that not showing up? Okay. 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 So I'm not sure why it's not showing up for Sam. What I will do is I will print off a PDF of this and then attach it to the slides. So if you're missing this for the work, I will give you guys a copy of this as soon as the stream's done on there. Okay, so continuing on here, I'm going to go through the basic process here. So T equals M1A plus M1G. And then we're going to take that, and I'm going to switch up colors. And now we're going to plug this in for T. And then we solve the rest of the way. So M2G minus M1A plus M1G equals M2A. And then let's see. M2G minus M1G equals M1A plus M2A. So just algebra from here. We're kind of just pulling and switching around here. I'm going to factor out an M1 plus M2, and I'll get M2G minus M1G over M1 plus M2 equals A. And that is the solution for part B. Sure. So back at the beginning here, each of these blocks, looking at their free body diagrams, each one of these has two forces acting on it. Okay. For block 1, we already determined in our free body diagram step that the tension has to be bigger. Right? So the tension going up for block 1 needs to be bigger than the weight going down. That's why I wrote T minus mg first, so I can set up this general direction as being positive. So going M1 going up, M2 going down, that clockwise direction, I guess, is what we're considering to be positive in there. Okay, cool. All right, then, so this is way number 1. It works perfect. Gives you well, excuse me, gives you full credit on the AP exam. But it is not my favorite way of doing this. Okay, if they want to involve calculus, Jess, they may ask you to write this as maybe a function. I'm thinking sub in A for dv/dt and then integrate or something like that. This one doesn't lend itself super well to calculus right now. Most of the calculus in CMech is going to be around kinematics or energy or rotation for those sort of things. So for this one, unless they want you to do something like have A being dv/dt and write an expression as a function of t for that, where you have to integrate, and that's the part I'm not positive about in there. Most of the APC mech tests I've looked at and have taught with, typically we'll use calculus with the kinematics, momentum, energy, and rotational sections. But really, there's not a ton of calculus for the forces. It's basically the same sort of stuff in there. Okay, so way number one, done in there. Let me show you guys way number two. This is my preferred way of solving it, and hopefully you guys will be able to see why once I get done solving this here. So let's use purple. This is way number two. Okay, and I'm going to hide out in the bottom left corner down here. We're going to look at the whole system. Okay. Looking at the whole system, if I look at this entire thing, all the tensions are inside my system. If I look at M1, M2, the string, the pulleys, all that stuff as one complete system, we've got basically the following setup. Okay. So we start off with F equals MA. The only two external forces are M2G and M1G. We know M2G has to be bigger. So that's my first term I'm going to write. Subtracting M1G because they're working in opposite directions. And then that is going to act and cause an acceleration on the entire mass of the system, which is M1 plus M2. And then that gives us the same line that we had right there on the other side. Okay, so while you can look at this block by block, and that works, you can also look at the entire system, and the entire system makes it a lot easier to solve this problem. All right, questions on that way? Just laying up again. Okay, so Sam, why did I add the masses? Because I'm looking at the entire system. This entire thing as my system. And because I'm looking at the entire thing, the big picture, I have to look at all the masses in that system. So because we had, yeah, okay, let me, this would all be quantitative. Okay, so let me jump over to a new screen here where I have some more work to do here, because I'll do it again for this problem in there. If I want to look at the entire system, as a free body diagram. And I know this is a fairly bad way of looking at it because you've got changing directions here. Realistically, we've got those two forces opposed to each other. The other thing going on here is, what object am I looking at them doing? Well, if I look at the entire system as being one solid object, this is really M1 and M2, the entire mass of the system. So when we say F equals MA for the entire system, we're talking about all the external forces, and we're talking about all the mass, which is why we had to add them together. Okay. All right. And then now the reason I like the system method a lot is because it works great with this third chunk, this explain why sort of setup. This one, notice how it's not saying in a paragraph answer or anything like that. This is simply explaining what's going on. This would be more the kind of just say what's going on here. The neat part about this is because we already did the work for this in the previous case. We said M2G minus M1G equals M1 plus M2 times A. This was the 2 block. Well, if we're looking at the third block, what did the third block add? The third block definitely did not add any external force. It's not pulling on the rope. Gravity's pulling this one down. Normal force pushes up. Those are pretty much equal to each other. Actually, they are equal to each other, not even pretty much. Those are equal. They're not making an external force going on here. It contributes nothing to the F side of it. But it definitely adds another mass to it. Right, it's not contributing to an external thing. The normal force in gravity, that block doesn't have any unbalanced forces on it in terms of just itself. We're connecting with the strings, now we've got some unbalanced stuff going on. But the idea I want to bring out here is that because of this, because we added in this M3 term, now we have a larger denominator with the same numerator, which means this is a smaller fraction. And that means we now have less acceleration. Okay, and that is one way that you could mathematically explain why the acceleration's got to be smaller with that 3 blocks. You could also do this perfectly fine without any sort of math involved here. Let's see, let me type out a response for that one. So saying I don't want to do math, let's do this qualitatively. So John, qualitatively, they're going to say something like, explain this without using equations. So you could say something like, actually, let me type this one out and we'll see how it goes here. Okay. Let's see if that works. Try this so we can read the whole thing. No, not the whole thing, just that. I just want this one to move. All right, so can I shrink this so it actually? There we go. Okay, so something like this would be perfectly fine to do for a qualitative sort of thing. Yeah, if you're referring to a law by saying, hey, there's this relationship going on here, it's inverse, it's indirect. When one goes up, the other one goes down, or something like that, that's perfectly fine for qualitative. Nowhere in this paragraph did I refer to we are using the equation in part B. We see that when we make the, no, I'm not referring to an equation at all. All we're doing is saying that, hey, acceleration and mass are kind of opposites of each other when the force is the same. So yeah, John, your explanation there would work really, really well for that. Yep, you can verbally reference this sort of relationship. The only thing is you're not going to say, you know, according to this equation, which I found on my reference tables, it means that blah, blah, blah. You're going to say, according to Newton's second law, acceleration's proportional to the force. Or, yeah, stuff like that. All right. I think we got time for one more of these. So let's do one that's slightly more mathematical in there, because, well, we haven't really done a ton of the more complicated math ones. There is a one on the, well, the community post. I threw one up there talking about tensions and strings and which one's the bigger tension, justify your answer sort of stuff. If you guys want to take a look at that and solve post a response by Thursday, I'll go on Friday and then comment them up and talk about what the best responses would be there. The link for that is in the slides, or you can just go to the community at Fiveable and then jump in from there. All right. So I think for the, let's go first. You can throw them into the, there's any CRAM session has a thread that's already set up for it. And if you want to post questions there, that's fine. I'm supposed to be getting my very own Fiveable email address soon. Once that's done, I will blast out an email to all you guys so you have my info, and then you can shoot me questions whenever we are apart. Okay, so yeah, last one for today. We've got a pendulum. It's got a bob. It's got some masses, stuff like that. Okay, numbers, 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 all these wonderful numbers. We're supposed to draw a free body diagram and calculate the tension in the string. Okay. The reason I'm doing this question, did I not? Oh, no, because it's published to the web. Yeah, sorry. We're going to have to be careful with that. In order for us to see it on Fiveable, it's got to be everybody gets published, but I will try to fix that. Can I quickly turn that off? Link sharing. Hey, that's a good idea. No, this view. Save. All right, thanks, Jess. That is now fixed and gone from there. The reason I chose this question on here is because with only 2 questions on your AP exam that count, they've got to mix different topics together. And this is a great example where you could pull in forces, circular motion, energy, and simple harmonic motion all into one question. So for right now, we're just going to do the forces part of it, but pendulums and springs and stuff like that, I would not be surprised if you see a question like that on the exam, because they tie in so many different units and different topics together. All right, but let's get this one done. How many forces do we have acting on this bob? There are 3 of them, correct. All right, tension, gravity. There are three. Yep, so let's go through. Easiest one, we've got tension. Sorry, we have gravity going down, not tension going down. Goodness, I need to go to bed. Gravity going down. We've got this tension here. I'm going to call it T1. And then another tension going off here that I'm going to call T2. And for the sake of, this should be a 30. Oh, that's whatever angle is there. It's a sketch. It doesn't have to be perfect. And there, I got to figure out what that angle should be. 60, I think. No, that should be 30. I don't know what I'm doing, guys. We're going to leave it right there. T1, T2, and some angle going on there. That is my take on the tensions. You also have the freedom to make up whatever symbols you want to for this. TH for the horizontal one, TS for the string one. There's lots of different options in there. What I want to get into is part B. Calculate the tension in the horizontal string. All right, so for this, we cannot do this in one equation. Okay, we cannot do anything that involves just one grand F equals ma and we're done sort of thing here, because these three forces do not all act opposing or parallel to each other. There is some perpendicularity in there. So we've got to turn and get a T2y and a T2x going through there and saying something like all the forces horizontally must be balanced because the bob isn't accelerating here. That means T1 must equal T2x, which is T2 sine 30. Likewise, all the vertical forces must equal 0. mg must be equal to T2y, which is T2 cos 30. And I'm getting those from the fact that vertical is adjacent to our angle, so that's our cos, and then the other one is opposite it, so we're using sine for that on there. And now we've got our system of equations. Solve one of these for one, plug it into the other one, and we are good to go. Since we're looking for the horizontal string, that is T1, I'm going to solve the bottom one for T2 and then plug it in. And then we take that and we plug it into here, and we get T1 equals mg sine 30 over cos 30, which is mg tan 30. And there is our answer for that one. All right, questions? Concerns? Anything else you'd like to say before we wrap this up? No, you could definitely do it that way, John. So if you wanted to say, like, I used sine and cos of 30, you could also very easily have said, well, wait a minute, that means that we can also do this. So I can also have this be T2 cos 60 and T2 sine 60. They will give you the same exact value because sine and cos are, or sine of 30 is cos of 60 and vice versa. So yeah, it doesn't really matter. I like doing the 30s because that's the angle they're giving me in the question, and it's one less thing for me to screw up. But yeah, it's perfectly fine to say, oh, well, if this angle's a 30, that means the other one's a 60, and we can go from there. So saying that, hey, if this is a 30, that means this is a 60, and then yeah, go from there. Perfectly fine. All right. Okay, so I'm going to upload these solutions as a PDF. That'll be attached to the last slide in the slides. And this recording will be on Fiveable, well, as soon as I get it done. I look forward to seeing you guys again next Monday. We're doing energy. And then, of course, Wednesday streams, 1 o'clock is open Q&A about anything. And Wednesday night at 7 is rotational stuff, I think. Something. Check the website. All right. Have a great night, guys. And yeah, I'll see you guys later.